Okay, so remember what we were talking about. We were in the middle of talking about a certain kind of series, right? We said that we just established, we were talking about series of particular form, like where you have you have two sequences and you're taking the product of those, the term-wise products, and then you add all those things together, right? And we had established the following theorem, that if you have two sequences, and B and R sequences, and so let me just say this way, let A and B and B sequences, if one, the sequence of partial sums of A(n), so let this thing be the sum from k equals 0 to n. That's the sequence of partial sums, right? If the sequence of partial sums of A is bounded, and 2, if Bn is decreasing to 0, right? Then the sequence of the sum of the termwise products converges. And we finished up with applying this thing to Leibniz's, to get Leibniz's theorem on alternating series. Right? You have these terms that are decreasing in magnitudes and alternating in sign, and then the sum is going to converge, right? Because you take the an as as the sign, and you take this thing as the bn as the magnitude, right? And the sums of the partial sums of the pluses and minuses is a bounded sequence, and the magnitudes are decreasing to 0, and so the alternating series converges. Right? And that's the last thing we do. Okay, and said that we're going to do one more. There's one more result along these lines. If you have Cn Zn a power series with radius of convergence 1, and if the C's are decreasing and they decrease to 0, so you have a decreasing, these guys decrease to 0, then the power series converges on all of the boundary excluding z equals 1. Okay, right, so you start off with this power series, and you're given that it has a radius of convergence 1, right? So you know that everything converges inside of here, and you know that it diverges outside of here. And you're wondering what happens on the boundary. Okay, you're wondering what happens on the boundary. If it satisfies these conditions, right? If the Cn are all real numbers that are decreasing to 0, then the thing converges on all of the boundary, except this place where it definitely cannot converge, right? Or it might, I'm sorry, you don't know. Maybe it does converge there, or maybe it doesn't converge there. Okay. It may well converge at 1 also, but by this theorem you get that at least it converges on the boundary excluding that point 1. Okay. So this would apply to that series that we mentioned before, right? This one, right? Because here you've got these 1 over n. The 1 over n are a decreasing series that go to 0, right? And so the theorem would tell us that this thing converges on all of the boundary excluding 1. Okay. So the proof, I mean, this is basically just a consequence of this theorem here, right? You take a sub n to be z to the n, take b sub n to be c sub n in the previous theorem. I'm sorry, first fix some z on the boundary that's not equal to 1. So choose your guy, choose your z, and we see that it will converge by looking at by taking our a sub n to be this, right? Because then summation, if we look at the sequence of partial sums, right? Sequence of partial sums. Right. This is z to the k from k equals 0 to n. Right. You recognize this, right? This is a geometric series. And if you remember from whatever, if you take the sum of a geometric series up to the nth term, you get 1 minus c to the n plus 1 over 1 minus c. Okay, this is just the sum of the geometric series. And if you look at the size of these guys, right? Look at the size of these guys. Well, this thing here on the top is smaller than 2, right? Because z has magnitude 1, right? So by the triangle inequality, this top is smaller than 1 plus 1. Right, so the top is smaller than 2, and the bottom we're just going to leave as is. Okay, so you get some number, right? That all of the partial sums of the z to the n of these guys, right, are bounded by 2 over the distance between 1 and z. So that gives us that that the partial sums are bounded, right? And then we have that the c sub n are decreasing to 0, right? And so we have convergence. Right. So summation a sub n, b sub n converges, right, like the previous theorem. Okay, so that's just a nice application of this theorem about products. Any questions about that? Any questions? We just plug things in. It's just an application of this result. Okay, so the next topic is also in series, so-called absolutely convergent series. Okay, so what's an absolutely convergent series? This is, I think many of you have seen this before. What's an absolutely convergent series? So definition, we say a series is absolutely convergent if what? If the sum of the absolute values converges. Okay, so for a non-example, if we look at -1 to the n over n, right, -1 to the n over n, well, that converges, right? That's convergent, but not absolutely convergent. Right? Because if you take the absolute value, you get the harmonic series. And we saw earlier by the p-test that 1 over n doesn't converge. If we so the main observation, if a series is absolutely convergent, then it converges. Okay. So, for example, like if I said, let's look at this this series, right? We have -1 to the n over n squared. Does that series converge? Yes. Right. Why? A few reasons. Why?
1 over n squared converges.
1 over n squared converges, right? So by the observation, which we haven't proven yet, you can say, well, you wrote this on the board, we're going to believe you. We take the absolute values, we know that that thing's convergent, so by the thing that we haven't proven yet, that this is going to converge. Can somebody give a better answer than that? You could say, well, by Leibniz's test, right, this is again an alternating series where the terms are decreasing in magnitude to 0. Right? So that's something you already know. Leibniz's test says that this thing converges. Okay, you've got an alternating series. Okay, but what if I take this series and I start throwing in like, something like this? So I've messed up the alternating series, right? Occasionally we get terms that are positive. So sometimes it's positive. Sometimes it's alternating, and sometimes it's not alternating, right? Then you couldn't use the alternating series test. However, by the result that by the observation we're about to make, then you know that this is going to converge, right? So you can mess up the signs as much as you feel like. You could say, make 3 of them positive, 10 of them negative, 15 of them positive, 20 of them negative, whatever. It doesn't matter. Because when you take the absolute value of this, it converges. Whatever however you change the sign, it's still going to converge. Okay. And in my notes, I say proof Cauchy Criterion. Okay. So take 1 minute and explain to yourself or somebody nearby why this is just a consequence of the Cauchy Criterion.
So that's Cauchy Criterion.
If it's convergent, then it has to be.
It's Cauchy.
Well,
Is it conversion?
always, depending on the metric space. But we definitely know that convergence is Cauchy. And so I think what we're saying is absolutely convergent. That means, okay, we can get to AN minus AN is less than alpha, right? So then that also implies, I think, AN minus AN.
Is this one less than that?
Let me think about that. I'm trying to think about it, yeah.
So it says like this is 4, negative 4, minus 2. Just 4 and negative 2. 4 plus 2. In that case, that one's bigger.
And then we can't do that.
你谁认识？我想找一下。Is this or that?
So this would be for, this is saying AN, this is saying, or AN, this is saying AN, Cauchy, this is saying AN, Cauchy. But you're saying that sometimes this would be bigger than this case.
Okay, would somebody like to tell me what the Cauchy Criterion says and why if it converges absolutely, it's definitely going to converge? You just need to say 2 words.
Two words.
Yeah.
Cauchy Criterion.
No. two more words.
Really 2 or like 3?
2.
Okay.
Can we just spit out words, maybe?
You're just going to throw out pairs of words until you hit it? Is that what you said?
Get that at some point.
The old monkey, infinite line of monkeys trick. Yes?
Triangle inequality.
Yes, triangle inequality. Triangle inequality, right? Because Cauchy Criterion says, right, given any epsilon, there exists a time such that when you're past that time, the absolute value of the sum from k from n to m of a sub k is smaller than epsilon. Right? That's what you need to show. That's what you need to show. And you already know that this sum is smaller than epsilon. Right? Right? Well, if this sum is smaller than epsilon, the other sum is smaller than it by the triangle inequality. Right? So we know this, but then this thing is smaller than that by triangle inequality. Right, so the n that worked for the absolute value series works for the original series. Okay. Any questions about that? Okay. So okay. So there's a theorem about series and arithmetic, and I'm not going to prove, but it's pretty straightforward. If you have a series that converges to A, and you have another series that converges to B, then if you can, the term-wise sum, you make a series by summing these guys term by term. This thing will converge to the sum of the series. The sum of the limits, excuse me. Okay. And the second part of the thing is that if you have some constant, some constant, then the sum of the constant times the series is going to be just the constant times the limit. So those are trivial things. I'm not going to prove this because those are like one line. They're very short. You can read it. Rather, we're going to prove the more complicated one. When you have two series, and you have something that converges to the product of those series. Okay. So let some A sub n, some B sub n be series. And let C sub n be the sum from k equals 0 to n of A sub k times b and minus k. Then we call the sum of the C sub n the Cauchy product of the two series, some A sub n and some B sub n. And what we're going to, so there's a result that we're not going to prove. What, why do we care about this thing, the Cauchy product? It seems kind of a strange thing, but here's kind of the ultimate theorem about the Cauchy product. Right? If these guys converge, and no, let me see this. If all three of these series converge, right? You have this guy, you have this guy, and you have the Cauchy product converges. Then the Cauchy product actually converges to the product of the limits. this is the theorem of Abel. We're not gonna prove this one. We're gonna prove something weaker than it. It's too hard for right now, but we'll prove something. We will be able to prove something along these lines, but not this full thing. Okay. So the Cauchy product, you see, converges to the product of the series. Adam, you're looking. No, you're okay. All right. Something else is bothering you. Okay. Right. So the Cauchy product actually converges to the product. Okay. So you might be wondering, what is this Cauchy product? What is the Cauchy product? And the way to think about it is, if you wrote these, think of consider the sum of a sub n z to the n, sum of b sub n z to the n. Okay. Suppose you have these two power series, right? And you just wrote them out. A1z, B2z squared plus dot dot b naught plus b1z plus b2z squared plus. And suppose you can multiply. You could multiply term by term. Right. So you have this infinite thing, and you just multiply it out as if it were a polynomial. Okay. As if you had two polynomials. They just happen to be infinite polynomials. Okay. In that case, you would get a naught b naught plus a1 b naught plus b1 a naught z plus so let me write it this way. A naught b1 plus a1 b naught z plus a naught b2 plus a1 b1 plus a2 b naught z squared plus etc. etc. Right now, let z equal 1 in this equality. What you get is that, right, a naught plus a1 plus blah 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 times b naught plus b1 plus blah blah equals this thing, right? A naught b naught plus a naught b1 plus a1 b naught plus a naught b2 plus a1 b1 plus a2 b naught plus and so on and so forth, right? And you see that these things are the this is your C0 in the Cauchy product. This is C1, this is C2, and C3, and so on and so forth. Okay. So, these things in the Cauchy product are really what you would want to add together to get the infinite product if you could multiply term by term. So it's sort of a valid guess as what kind of sum will converge to the infinite product. Okay, and in fact, there's this theorem of Abel saying that if these guys converge and the Cauchy product converges, then the Cauchy product converges to the product. So it really is the right guess. Okay. So the Cauchy product is just this sum on the right hand broken up in terms of the guys that correspond to different powers of z. Right? C0 is the coefficient that corresponds to z to the 0. right? This corresponds to z to the 1. C2 corresponds to coefficients of z squared, and so on and so forth. Okay, so so that's what the Cauchy product is. Okay, so we are going to prove not the theorem of Abel, but a theorem of Mertens. Which says the following. So it's not as powerful as the theorem of Abel, but it's the one that we can prove right now. So here it is. You have some series, right? The first one converges to A, the second one converges to B, and C sub n is defined as the terms of the Cauchy product. Then, if one of the series converges absolutely, then the Cauchy product converges to the product of the series. So it's a little bit different from how the other one, how Abel's theorem goes, right? Here we're saying that both of these guys converge, and one of them converges absolutely. And then you know that the Cauchy product converges, and in fact converges to the product. Okay. In this one, we have to actually assume that the Cauchy product converges to start off with, right? You don't say if these guys converge, then this guy converges to the product, right? But rather you have to assume that all three of these guys converge first, and then it converges. So it's slightly different. Okay.
Why is this one weaker?
It's weaker because we need absolute convergence. Right? We need to put a stronger condition. We need them both to converge, but we need one of them to converge absolutely, which is harder to do. Okay. Okay. So here's the proof. I didn't know if anyone looked at it. Did anyone look at the proof? Yeah. Okay. Do you have any comment on it? Complicated. Yeah.
In terms of algebra.
Yeah, it's mainly a lot of algebra. Yeah. It's mainly a lot of algebra, but once you get through the algebra, then it's not so bad. Yeah. Okay. So here's the proof. Great. So let A sub n, B sub n, and C sub n be the partial sum sequences. Okay. Let these guys be the partial sum sequences of the corresponding series. Okay. Let beta sub n be the difference between the partial sums and their limit for B. Okay. So the B sub n are going to converge to B. The beta sub n is the error, right? How far off you are from B. And then we introduce this other term, gamma sub n, and that is A naught beta sub n plus A1 beta sub n minus 1 plus A sub n beta naught. And that term should be kind of mysterious. Like, what is this term? Okay, but it's an easy calculation to say that gamma sub n is the difference between C sub n and A sub n times B. right, we're hoping, right, our hope is to show that that C sub n, capital C sub n, turns into AB. Right? Capital C sub n converges to AB. Okay, and you see that here we have capital C sub n minus A sub n B. Right? And so if we can show that this thing goes to 0, then our hope is realized. Right? As n goes to infinity, if this becomes 0, that means that C does become A times B. Right? Because A sub n turns into A, and C sub n turns into C. Right? We want to show, right? We want to show that C sub n, the limit of the C sub n, is actually A times B. Right? That the Cauchy sequence, I'm sorry, that the Cauchy product turns into the product of the other series. Okay. So let me just show this calculation. Right? Let me show the calculation. Well, you say, look at C sub n. C sub n is, by definition, right? C sub n is A naught B naught plus A naught B1 plus A1 B naught plus dot dot up to the nth term of the Cauchy product. Right? A naught Bn plus A n B naught. Jonah, you're looking a little, if I may say, you look a little lost. Yeah, okay. Yeah.
I just don't see where you got the C sum. I just don't really see where you get like any of these from, to be honest. But.
Okay, so don't worry. That's that's all right. So at this point, the gamma sub n should be mysterious. Okay. So, and here's what we're about to show. We've created this gamma sub n guy. We're going to show that this gamma sub n guy actually is the difference between C sub n and A sub n times B. Okay, so proof by calculation.
And it's C sub n we just calculated a minute ago, right?
Yeah, C sub n we know. C sub n is just the partial sum of these guys.
It was the thing you did when you substituted z equals 1.
Yeah. It's from that. Yeah. Okay. So we're summing. This is your C0, C1. Plus Cn, right? So it's the partial sum of the Cauchy product. Okay, and we're just going to rearrange it, and what we'll see is that what we'll get here is AB plus gamma sub n. So we just do a little bit of rearrangement. We say, okay, let's use your childhood friend, the distributive property. And factor, look at all the terms that involve A naught, right? You've got B0, B1, up to Bn, right? So that's the partial sum of the B's. Okay. B sub n means the partial sum of the B's, right? So here we've got B naught, B1, up to Bn. That's that partial sum from 0 to n. Okay. And you've got A1. Well, A1 doesn't go up to, A1 goes up to Bn minus 1, right? So you get here the partial sum up to n minus 1, right? And for A naught, we get all the way up to Bn, but for A1, we go from 0 up to Bn minus 1, right? And then for A2, we go up to Bn minus 2, and so on and so forth. A2, Bn minus 2, plus dot dot dot, An B0. Okay, so it's just a relabeling at this point. We do another relabeling. We say this B sub n is the same thing as B plus beta n. Okay, so we just replace those guys. B plus beta n, B plus beta n minus 1, and B plus beta naught. Okay, so it's just by definition. And then you see, okay, well, look at everything that's multiplied by b. Well, you've got b times a naught plus a1 up through an. So that's the a sub n sum, partial sum. Right? And then you have what's left over, you see, is what we call gamma sub n. Right? We got a naught beta n, a1 beta n plus n minus 1, dot dot dot, a n beta naught. That's this thing here. Right? So that gamma sub n is just the leftover. Okay. So observe. It suffices to show that gamma n goes to 0. Right? Because if that happens, that means that C sub n, which turns that C converges to A times B. So okay, so let's do that. That's actually not too bad. So it's just a matter of okay. So let's show that. So let's look at this thing, gamma sub n. Okay. Gamma sub n, by the triangle inequality, is smaller than a naught beta n plus a1 beta n minus 1, which is beta n minus 1, plus a sub n minus 1 beta n plus 1. So I'm going to actually, I'm going to have some bad board work right now. And I hope you forgive me for it. So I'm just writing gamma sub n here. Okay, I just wrote out the terms, but I'm writing out something that happens along the way. Okay. So like at some point you're going to get an n plus 1 term, an n term, all the way down to 0. Okay. The reason I'm doing that is because I want to split it using the triangle inequality. So this thing is less than this plus this. Okay, so what's the point of doing this? What's the point? So think. The B sub n are the difference between capital B sub n and B. Right, they're the error for the second series. So we know that error goes to 0. Right. They're the difference between the partial sums and the limit. Partial sums converge to the limit, so these guys go to 0. These guys just go to 0, so actually, sorry, let me say something else first. The A sub n converges absolutely. Right, so this thing converges absolutely. Call their limit the absolute limit alpha. Okay, you sum all the absolute values of these guys, call it thing alpha. Okay. So you know in particular that the size of each of these terms is smaller than alpha. Right? Each of these guys, all of these guys is smaller than alpha. Okay, now I'm going to say what I said before. The beta sub n go to 0. So you know that there exists some n such that for n bigger than n, the size of the betas is smaller than epsilon over alpha. Right? Because these guys go to 0. Right? So you can make them all tiny.
Where did you get the alpha in there?
Alpha is this alpha, the alpha from the...
Yeah, why do you divide beta or epsilon by alpha?
You'll see in a second. Right? When we're gonna control the size of this thing. Okay. So I just wrote an epsilon without explaining where the epsilon came from. So fix some epsilon first. Okay. And what we're gonna see is that this thing is smaller than epsilon, basically. We can make this thing smaller than epsilon, right? Which is what we hope. We want to make sure that this thing is 0, becomes 0. Okay. Okay. So, well, this thing is smaller than this thing, right? But if you look at this guy here, right? Each of these terms is smaller than alpha, right? Hold on a second. I'm messing things up. No, I'm sorry. Sorry, I said something wrong earlier. Let me erase this thing here. Sorry. That's not what we want. Okay. So look at this thing here. Right. Yeah. So this thing is smaller than absolute value of a naught times epsilon over a plus the absolute value of a1 times epsilon over alpha dot 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 absolute value of a n minus 1 times epsilon over alpha. Right? Right, by the triangle inequality.
So every bn, all the betas are
Each of these guys, right? So all of the betas have n's that are bigger than n, right? It's n plus 1, n plus 2, up to some beta n.
Mm-hmm.
Okay. So all of these guys are smaller than epsilon over alpha. Okay. So we replace them all with epsilons over alphas and use the triangle inequality, right? And we get this thing here. Okay. Right. But that is that in turn is smaller than epsilon over alpha times the sum of all of the the full times the full series, the full absolute series, right? But we said that we call that thing alpha, right? So this is smaller than epsilon.
That's just the top.
Yeah, that's just the thing in the circle here. That's just the thing in the circle here. Okay. So what we have at this point is that that the size of gamma is smaller than epsilon plus these last guys. let n go to infinity. So let n go to infinity. Okay. Now, these terms here, so notice that since the a sub n, right, since the a sub k go to 0, right, as k goes to infinity, this term is going to vanish. Right, this term vanishes. The term on the right goes to 0. Does that make sense? Right? Like you're let me say it.
Can't you just say that for everything too? Like the top line, as n goes to 0, all those terms vanish.
No, because here you have an infinite number of terms. Right? As n goes to infinity, you're actually increasing the number of terms. How many terms do we have here? There's only n terms, only capital N terms here. Right? There's n minus capital N. So this thing here is, so n minus, so this thing here is smaller than, say, the greatest of these guys. The greatest of these guys times this sum, beta n plus beta 0. Right? Right. Now this thing is just some finite number, right? Call it m. This thing is just some finite number, right? We fixed our n over here. We fixed our capital N over here. Okay. Now we're letting little n go to infinity. As little n goes to infinity, nothing happens to this, right? This doesn't change. This is a constant. Right? This is a constant. But as n goes to infinity, this thing goes to 0. This max goes to 0, right? Because you're looking at the max of, n terms from a sub n down to a sub n minus n, right? So as n goes to infinity, this thing goes to 0. So goes to 0 as n goes to infinity. And so what you end up with is that, so the limb sup of this thing is smaller than or equal to epsilon. Okay, but epsilon was arbitrary, and so we know that this is going to be 0. Sorry for messing it up a little bit. Right? But it should be okay now. Are there any questions? go on. There's no questions. Are there any questions? Jonah?
I think I'm just going to watch this over again.
Okay, okay.
I think that's more useful.
Okay. So, you know, we take this thing, we break it into two parts, right? In the first part, we've chosen n so that all of these betas are small, right? All of the betas are small, smaller than epsilon over alpha. Okay, right? You factor those. Using the triangle inequality, you factor those guys out, and using absolute convergence of these guys, you get that thing is you can make this thing small. And then the second part is just using the fact that that the a sub n's go to 0, right? Because the sequence is, because the series is absolutely convergent, by the nth term test, you know that all the terms have to go to 0, right? Okay, and so what you have is these guys where n is some fixed number, right? So you're looking at things where these things where the coefficients are in a fixed range of your sequence of a sub n's, right? They're just there are n terms here, right? There are n terms here, and you let little n go to infinity, right? So they all travel together to infinity, right? So you can make these guys as small as you want, right? You can make these coefficients as small as you want, and you're multiplying these coefficients. Using the triangle inequality again, you're multiplying these coefficients by a finite number, right? You're multiplying these coefficients by this thing, which is just a finite number, right? So you have some constant multiplied by something that you can make as small as you want. So that goes to 0 also. Okay. So there's one more thing in the series section, which is about rearrangements. Okay. So all a rearrangement is you've taken your series and you've changed the order. Okay, so you're taking the series and you're adding the terms in a different order than you started. So let k sub n be a permutation of the natural numbers. Okay, so you have some sequence, and you've taken the natural numbers and you've changed the order, right? Maybe like you have I don't know, like 2, 1, 4, 4, 3, 6, 5, blah blah blah. Right? And that's you've rearranged the natural numbers, right? And let a sub n prime be a sub k n. We call the sum of these rearranged guys a rearrangement of the original series. Okay. So so Riemann gives a theorem of Riemann that says if you have a series and it converges, but it does not converge absolutely, then for all alpha and beta, where alpha is less than or equal to beta, and they are extended real numbers, there exists a rearrangement an prime such that the lim inf of the sequence of partial sums is alpha, and the lim sup of the sequence of partial sums is beta. What does it say? It says that you can rearrange your series to converge to whatever number you desire, right? So, like, we know, for example, that this series doesn't converge. This series converges by the alternating series test, but it doesn't converge absolutely. And what Riemann is saying is that you can rearrange it so that so that this converges to 10. You can rearrange it, and the rearrangement will converge to 1 billion. You can rearrange it so that it converges to infinity. You can rearrange it to whatever you feel like. Yes, Mia?
That's not make any sense.
That doesn't make any sense. I wasn't going to prove it because it's kind of it's not that interesting. I mean, maybe I'll prove it next time.
Okay.
But yeah, so that's what it says, that you can rearrange. If it doesn't converge absolutely, then you can rearrange it to converge to whatever you feel like.
I mean, I guess without a proof, why is that? Like, is there any kind of like reason why I should believe that that's the case besides just the fact that you told me that it is?
Right.
I remember seeing this theorem before, but I don't think I ever saw a good reason for why it's true.
Okay. I'll prove it next time. I think people seem curious about it. It's cool enough that I think it merits some of our time. But let me prove something much simpler, which is that if an infinite series converges absolutely, then any rearrangement of it also converges, and in fact to the same value. Okay, so here we go. So suppose we have some epsilon, and suppose we have some epsilon. Choose n such that for all n bigger than n, the sum of the absolute values of the a sub k, when k equals n to m, is less than epsilon. Okay, so that's to say that the terms from 0 to capital N contain the meat of the series. Okay, so now take any rearrangement. Let's say a sub n prime is a sub k sub n, using the previous notation. Okay. And then choose an n prime such that a1 through an are all contained in ak1 through akn prime. Okay. And notice that right there that n prime is greater than or equal to n, because you have to have there are n prime terms here, and there are n terms here, so you have to have n prime had better be bigger than or equal to n. Okay. Now let Sn prime be the partial sum sequence for the a primes for a prime k equals 0 to n. Let Sn be the partial sum sequence for the original sequence, and let's look at so then if n is bigger than capital N prime, and we look at the difference here, Sn prime minus Sn, what you see is that you're going to have these terms ak1 plus akn, right? And you're subtracting off a1 through an, right, where n is bigger than n prime, which is bigger than capital N, right? And so these guys contain all of the these guys that contained the meat of the original sequence, right? So when you subtract off these, you have some cancellation, and you're going to end up with terms. Some of them are positive and some of them are negative, but you're not going to have any terms that have all of the terms are going to be past. All of the terms indices are going to be past capital N, right? So you take take the sum of the absolute values of all those guys, and that you see that this thing is going to be smaller than the sum of the absolute values of some ak, where k goes from some m to n, right? But m is bigger than capital N, and so this is less than epsilon, right? Okay. So in other words, we can make the the partial sum sequences as close as we want, and so Sn minus Sn prime goes to 0. In other words, the rearranged sequence converges to the same limit as the original sequence series. Okay.